Here we go.
We're live, baby.
Yeah, we are live. Now, yesterday we did our test, but we started to talk about projectile motion. And the one concept, I want to say, compared to some of the vector problems that we did from our first batch, where you were really moving all over the place and you had to break multiple vectors into pieces, projectile motion is not going to be as elaborate as that. But you have to be comfortable with a concept that I brought up Tuesday, which could be referred to as vector independence. And really, this only comes into play when you're talking about two or more vectors. And for those that remember, what's the key angle? 90 degrees. If two vectors are perpendicular to each other, that means that what happens in one dimension does not affect what happens in the other dimension. And sometimes that can be challenging for people to be okay with, because they'll want to say things like, but aren't things still happening in that other dimension? And the answer is yes, but because it's acting at a 90-degree angle, it's not impacting in terms of making something in the other dimension any bigger or smaller, and it just stays the same. Or whatever behavior you're talking about continues to happen unimpeded by the other dimension. Now, I want to point out one thing, because I think most people have heard comments about one dimension, two dimension, three dimension. And the thing that we connect them to most often are graphs or graphing systems that you are taught in math. But the thing that I would point out to you is that when you go from one dimension to two dimensions, how do you orient your two dimensions? What angle separates them? 90 degrees. And when you go to three dimensions, how is that third dimension angle-wise compared to the two that are already there? If you think about it, two dimensions we could put on here. Where's the third dimension? 90 degrees to the other two. So the whole idea when we talk about multiple dimensions, at least 1, 2, and 3, every additional dimension always gets added 90 degrees to the one or ones that are already there. Okay. Now the only way that I can think to kind of try and set the stage for doing some projectile motion problems is to go through an example of something that's the most basic kind of projectile motion problem. And that is, you have an object and it's at an edge and it is being projected horizontally off of that edge. So it is not at all going up, it is not going down, it is just being launched perfectly horizontal. Most people are taught in their math classes, when you do quadratic equations, they usually apply that to projectile motion, because the characteristic shape of anything in projectile motion is a parabola. But that parabola, when we're going to break it down today, is really generated by two things happening at the same time. Now, in order to try and, I'm going to try and do a better job on this presentation. First, I want you to imagine, let's say we were on just a totally flat surface, and something had interacted with this object to get it up to a speed here, and then at this moment that interaction ends, and And we're in a physics perfect world, which means there's no friction. So if you wanted to say, yeah, it's like somebody shoved this thing, but now they're not shoving it anymore, but we're in a frictionless environment. How will this object behave as it continues to move across the surface then?
Friction.
And it's frictionless.
Just going forever.
Okay, will it go any faster? Will it slow down? What do we call that? What? Constant velocity. Okay? Now, when we look at this, what dimension are we talking about? It's only moving this way. So we would refer to it either as the horizontal dimension, or if you were in a math class, what letter would you assign it? X. Okay? So here is, let's see, I'm going to start this here. Horizontal. One of the things that you'll need to remember is that when we talk about projectile motion, and it's two-dimensional, things will be moving up and down and side to side simultaneously. But when we look at the behavior of the object horizontally, as it goes through its pathway, it will always be moving with a constant velocity. How many equations do we have for constant velocity? One. What is it?
Distance over time.
Okay. We have v equals delta x over t. Now, because we are eventually going to be dealing with objects that can move in both dimensions, we need to be a little more specific about this v. Because this only applies, this idea only applies to what the object is doing horizontally. So we are going to have to be pickier about this v, and the way that we do that is we put an x there. Okay? Now, going back to my example up here, I said, well, let's just pretend it's only going horizontally the whole time. In the end, we're gonna have to mess with that a little bit. So now let's do something else here. Let's put the object at the exact same spot, but let's say we are not shoving it to the right. All we're doing is dropping it. What will happen to it? It'll go down, and what will be happening to it as it goes down? It'll be accelerating, because what's in this dimension that isn't in the other dimension? Gravity. Now, some people, when they think of this object going horizontally, they'll say things like, well, doesn't gravity do something? It's like, not if it's on a flat surface and it's frictionless, it just keeps on going. And you could say, well, isn't gravity there? Yes, but it would be an arrow that points straight down. And how many degrees is that away from this object moving? 90. And that means gravity doesn't affect that aspect of the object at all. But now if we drop this guy is going to go down. And because it's accelerating, this is where we can go vertical. We have acceleration. How many different equations we have for that? 4. All right, well, we're going to put them all out here. Vf equals at plus vi. Then we did delta x equals 1/2 t vi plus vf. Then we did delta x equals 1/2 a t squared plus vi t. And then we had 2a delta x equals vf squared minus vi squared. Now, when we initially played around with both of these, we limited ourselves by saying we are only going to deal with a one-dimensional problem. And that meant if an object was moving side to side, it was not allowed to go up and down. Or if it was moving up or down, it was not allowed to move side to side. The thing that makes projectile motion a little more complex is we are letting the objects do both at the same time. That means these equations right here for acceleration, what dimension do we have the acceleration going on here?
Vertical.
In the vertical. Can somebody point out one letter that you would say, okay, that's not going to work?
B.
No, I'm thinking of another one. Why is this very inappropriate now? What should it be? It should be delta y. Now, if you were to ask me, well, why did you start it with delta x? When we first did this, we didn't let objects move right or left as they were going up or down. So we just called how far it moved delta x. But in this scenario for projectile motion, we have to be much pickier when someone says, how far did it move? Well, what dimension are you talking about that motion in? And so if someone says, oh, let's do it this way. What is the difference between someone saying the delta x for an object was 4 meters versus the delta y for an object is 4 meters, now that we're bringing this up? Because if someone says, delta x, delta y, both 4 meters, no difference, there is. What is it?
The dimension.
Correct. If someone says the delta x for my object was 4 meters, and let's specifically say it's positive 4 meters, what did it do then?
Moved 4 meters right.
It moved 4 meters horizontally to the right. But if we were to say the delta y for my object was positive 4 meters, what did it do? It went up 4 meters. Okay? Those are very different things, even though the number is exactly the same. It's because it was in different dimensions. Now again, before we got to this point, we didn't let objects do two things at the same time. So we just called every going from here to there delta x. But now we have to realize, okay, I got 2 dimensions. So that means there's a difference between a delta x moving horizontally and a delta y for the vertical dimension. But from a vector perspective, the plus and minus still mean the same thing. So positive 4 delta x, right? Negative 4 delta x, left. Positive 4 delta y, up. Negative 4 delta y, down. So that idea of what the plus and minus represents kind of still tracks. Now there's one other thing that we have to do. And this is where, remember when we first presented this, we just said, oh, v equals delta x over t. Now the delta x we didn't have to change because this only applies to the horizontal dimension. But what else did we have to add to be more specific? We had to add the x so that we understand that this vx only refers to the horizontal or the x component of the velocity of an object. So what are we going to have to do over here?
Any y?
Okay, anything that is really in the y dimension, we have to add a subscript of a y to. And so that also applies to the VF and the VI.
What about time? Time's the same, isn't it?
Ooh, hold off on that one. You're jumping way ahead. In a good way.
Okay.
Okay, but I'll go ahead and say we are going to come back and talk about time. And we're not going to put anything, no subscript on time, because you kind of brought up the point that we'll try and hammer home here in a moment. Okay, so what we're going to do is I'm going to take you through, we'll call it a thought experiment here. And I'll change colors. This might. So now I have to have you think of something here. How many of you know what like a multiple exposure picture or is? No?
Like when it's like a composite over a long period of time.
Yeah, it's like taking a picture of like the same thing multiple times, but if I'm in one spot and then it's going to take a picture of the exact same thing like 1 second later and I move over here in that 1 second, you'll see me twice. And then if it keeps taking pictures with that same, this is kind of lost on the fact, do you guys even know what, you guys know what film is, right?
Like
Okay.
The physical.
The whole idea of a multiple exposure is you never advance the film. So you keep taking a picture of the same thing, and if nothing ever moves, it still looks the same all the time. But if you have something that kind of moves around between exposures, you get multiple images of that thing that appear. Now, today we just do slow-mo, you know, when we want stuff like that. But let's pretend we're going back to this object here. We're just moving horizontally, and we've already established that it's going to be moving at a constant velocity. And let's say that I'm going to take a multiple exposure of this 4 times. And the exposures are going to be separated by the same amount of time. We could just say 1 second. So it'll be like click, 1 second, click, 2 seconds, click, 3 seconds, click, 4 seconds. So I'm going to get multiple exposures of this, but they'll always be separated by 1 second in time. What are the multiple images of this thing going to look like in that picture? What?
I don't know, you're just gonna have like more circles going down the line.
There'll be more circles this way.
They'll be evenly spaced.
They'll be evenly spaced. So if I draw this, it would look like this. And I'll do that for our first. I'm going to try my best to be good about this. It would look like this. The separation between these would be the same. Okay? Same concept of multiple exposure. This object, I'm letting it fall. But I'm still going to separate my exposures just by 1 second. What am I going to see?
You're going to see more of them at the top and less at the bottom.
Okay, which means what's happening about their separation?
They're getting farther apart.
They're getting further apart, and if someone goes, well, why would that be happening? Why is that?
Acceleration.
Which means what about the velocities down here compared to up here?
They're higher.
They're higher. So if I'm going to, now this is where I'm kind of making this one up the best I can as I go along. So my first exposure might be here. The second one,
Is it kind of like that experiment we did with the dropper and
Yeah.
the receipt
yeah,
paper?
when we made the little spark, with the spark machine.
How do you get your dotted lines to be like so even? Like when you do it, can you tell? that
It's
you're,
my
like, saving dots?
architectural drawing from high school that's the magic here for me. The one thing that I learned from I don't know if I passed this tidbit along, because I do remember I shared this in one class. When I took architectural drawing, they did have a small unit where, what do you do if you have to do this freehand? Because architectural drawing is all about straight lines and making things, you know, nice, curves nice, and circles, you know, nice. And one of the things that I have learned, and sometimes it's hard to really buy into this, if you want a line to go from one point to another, you can go ahead and put your writing instrument here. Where do you look?
I don't know, to the right.
At your pencil?
You look at that place that you want to end up at, and you don't try and follow this. And it's like saying, you mean I have to trust that I'll just go right to the line?
I'm gonna try that.
And the truth is that people are usually pretty decent about getting somewhat straighter than if they're trying to draw, like watch the thing as it's being drawn. I don't know how many,
Like-
anybody mountain bike?
No.
Oh, no mountain
My
bikers in
dad.
here?
Yeah, my dad does.
When you mountain bike, when people say, where should I look? You don't look right in front. Because when you do, if you see something, it's like if you see a big rock coming up, you don't keep looking at it. You look at it like 30 feet down the road, but you don't track it in because you end up losing sight of where you're going, and you're more likely to actually bump into it than avoid it. It's like your brain knows, okay, got to get out of the way. It's hard to do sometimes because it's like you have to trust yourself.
No, I meant like when you draw like dotted lines, you can't even like see that your hand is going like this. It just like looks like you're just drawing
Oh.
straight.
Years of teaching
Yeah.
experience. I don't know. Okay, so in this picture, we have two multiple exposures, but of two different things. An object that is horizontally going at a constant velocity, and an object that is freely falling to the earth. The cool thing is, if we are projecting this object off the edge, both of these are happening at the same time. So, after 1 second, how could I draw, and I'm going to do this in red, how could I draw my object where it would be if I was actually projecting it off this edge here based on what I've already drawn? Anybody have an idea? Go ahead.
Are you gonna like connect where
Yeah.
the first one
It'd be
is?
like I come over here, I come down here. That's where the center of my object would be. So after 1 second, that's where I'd be. After another second, that's where I'd be. After a third, that's where I would be, and that's where I'd get.
And that's correct.
Now, when you're in math, you don't learn about projectile motion this way. This is how, and this one here, I will admit, this one is already too far down. If we were really going to do this accurately, this one would be shifted up much higher because you wouldn't drop as far in that first second. So I'm exaggerating this, but you can see that's where our idea of a curve comes from. It's two things that are actually happening simultaneously. It is this object wanting to move at a constant velocity in a horizontal plane, while at the same time gravity is pulling it down, causing it to accelerate vertically. Now, how does this deal with like vector stuff? If we were to ask, what is the velocity at position 1 here? We would be drawing an arrow that would look like that. At position 2, it would look like that. At position 3, it would look like that. This one would get like super steep, and literally this one would go off the whiteboard. And if we were to break this into the component vectors, the thing is that the component vector horizontally, oh, damn it.
The plumber?
No. Well, it says potential spam, so we're just going to let that go. The x component of each of these breakdowns is always the same. And that's a reflection of the fact that this object is moving at a steady speed horizontally. But the vertical piece keeps getting longer and longer and longer, and that's a reflection of the fact that gravity is causing this to pick up speed vertically. So when someone says, hey, as an object is projected through the air and it's on its way down, what does it do? If someone says it picks up speed as it's on its way down during the trajectory, not an incorrect statement, but there's more to it than that. Because if you're having to get picky about what is it doing horizontally and what is it doing vertically, horizontally, its velocity always stays the same. The reason that its overall velocity changes is because its vertical velocity is changing due to the influence of gravity. But because gravity is 90 degrees away from horizontal, that's why gravity does not affect that horizontal piece of our object. Wow, this crap's good. Okay, now, coming back to the equations, Ariel brought up the t thing. Why don't I have to do a tx and a ty?
Because it's not the same for both.
It's the same for both. It's impossible to have, oh, well, I was horizontal this and y. You're in projectile motion or you're not. And so this is realizing that this t doesn't get an x or a y, which means this t for our constant velocity is the same t in all of these equations, is a critical piece, because when you go to problem solve, they usually don't give you enough information for both dimensions, but they'll give you enough information in one dimension that you could figure out a t that you could then take over to the other dimension and then keep, solving more things about your object. We'll see that quite a bit. Now, I gotta go another color, orange. Parametric equations.
No.
This is just like gee whiz, like wow, that's so cool. In parametric equations, this is going to be super compressed up here. When we usually deal, and I'm only applying this to kind of this situation, when we usually play with a coordinate system, we do x and y. And what we end up saying is, well, each dot or each position is an x over and a y. And, well, how do you figure out y? We traditionally say, well, you figure out y because there's a function of x that when you want to know where am I when x is 3, there's an equation that you put the 3 in that you calculate something from that tells you what the y is. So literally, and more correctly, this, I don't know, has anybody ever seen that ordered pair version before?
Sure.
That xy is really x and then f of x. Now, in a parametric equation, there's actually a third variable that you can't plot on this. But that third variable is part of both of the dimensions that you have on this. What's our third variable? It's the t. So when we say, what is that spot right there? We don't say it's x. We have to know what the t is for that spot. But once we do that, there is a function that they call x of t. So if you wanted to know where is my object after 3 seconds, and you don't actually show 3 seconds on this thing, but you put a 3 into your function for x, and it gives you a number, that's the x coordinate. And for the other one, you have a different equation for the y coordinate, but it's a function of t. So the idea is when you want to know where anything is in this scenario using a parametric equation, the thing that's changing is this variable that's actually not on the graph, and it usually, in most applications, it is time. And the idea is at t equals 1, you calculate an x and a y, and you plot it like you normally would an x and a y. But you don't just choose x's or y's, you choose a time in space that you want to know where objects are at.
So your x of t would be a velocity equation and your y
Correct.
would be an acceleration
So
equation?
if we were doing this here, our x of t would literally be vx times t, because that would give us the x value for where our object is at. And for our y, when you look at this, you go, whoa, I got choices. But the most common one that you would use would be this one here. Because you put a t in here, this is a set value that you would know, and ay is negative 9.8 if you're doing meters. So the most common function that you would use for the y coordinate would be this thing that we call equation 3.
Are we going to be doing word problems with diametric?
No, but it's cool, so that's why I'm bringing it up. And I want to say for people who do computer programming, this is really useful because when you're saying, look, in my game, time is going to be passing, and I need to be able to tell things where to go as time passes. This is how you would program in where to put things, because you don't say, let me determine whether player 1 wants to go from x equals 1 to x equals 2. You want things flowing with time. Now, I'm going to bring up one last thing about this. Have any of you ever heard, because I say we live in 3 dimensions, anybody ever heard that, no, we really live in 4? What's the 4th dimension? It's time.
Yeah.
So the idea is that our world is a 3-dimensional space that we move around in, but the 4th dimension is time that is constantly, moving forward. Yeah.
So what if you have a wind blowing it in another direction? Would that be a 4th dimension?
No. What you would have to do is incorporate the effect of that wind into the separate x and y dimensions, and it would become part of the complexity of the function that would tell you exactly where things are. And that's an excellent point. Anybody golf? Oh, damn it. I don't have any golfers? Okay.
Mini golf.
What?
I said I've done mini golf.
Oh, okay. No, this is more about driving, because most people, if you get into simplistic applications of projectile motion, they will say, oh, it's always parabolic in nature. Well, if you kind of model a drive in golf perfectly on a computer with no real life influences, it would look very much like this. But if you've ever seen a drive actually done, it does more like this. And that's because vertically it behaves exactly the same as the black curve, but horizontally there's wind resistance. And as the golf ball tries to go through the air, this idea where I said, oh, the velocity, horizontal velocity stays the same all the time. Well, in the real world, like in golf, not really. Because initially, as the ball is going fast through the air exerts more influence against it, so it actually causes that horizontal velocity to slow down a little bit, but vertically it's still doing exactly the same thing, so it just doesn't go as far, and it looks like it kind of peters out at the end and then just drops. So again, this can get really complicated in the real world, and there are ways that you could deal with it. We're not going there. We're going to deal with ideal objects being projected. Okay, I think that's it. Any questions? Okay. So tomorrow, what we're going to do is we're going to handle this like that first batch of problems that we had you do the other day. I'm going to pick 3 or 4 of our projectile motion problems. I am going to walk you through the setup of those, trying to highlight how is all of this stuff. Oh, I forgot something, but I got to erase all this. So don't put stuff away yet. Because I've kind of brought in vectors a little bit, but I haven't given you, why was all that vector crap that we did so important? Some of the problems, we will have an object that is projected at an angle. Where they'll say, like with a golf ball, they hit a golf ball with 27 meters per second of velocity at an angle of, I don't know, we'll say 18 degrees. And then they're going to ask you questions like, how far does it go? How high up will it go before it tops out? That kind of stuff. Why can't we why will 27 not go anywhere over here?
That's not the time, it's
No. Because if I ask what is 27, what variable would you tell me it is?
Vi.
It is a velocity. I'll give you that. But what's the problem?
It's in
Non-directional.
This is a two-dimensional velocity. So what do I need to do with this before I can start to plug anything in over here?
Horizontal.
De-dimensionalize
like
it.
the FY.
What did we call that?
Resolution.
VY, VX, whatever.
You could either call it, I need to resolve the
Yeah,
vector,
that.
or you could say, I need to find my Vx and my Vy, and what specific Vy will this be if this is right when the golfer is hitting the problem?
VI.
Initial?
It will be the initial Y. Because during the course of its trajectory, the vertical is going to be fluctuating because of the influence of gravity. But our assumption is once we can figure this out, it will stay the same throughout the problem. Oh, see, now this is why you need to be comfortable with all that stuff that we did before. That anytime you have a vector that somehow you're given an angular measure associated with it, you're not going to be able to use the direct magnitude of that vector in any of your equations. And what you're going to have to do is to break it down into its horizontal and vertical component, and those are the pieces that will then allow you to start to attack the problem. Because we don't have equations that are two-dimensional equations. We only have equations that deal with the vertical dimension or the horizontal dimension. And if anybody goes, well, I've seen stuff that can do two-dimensional. Probably what it's doing is this behind the scenes, but you can program this stuff into a calculating device that is very quick, that can like do it what appears to be in real time, but it's still doing exactly the same thing. But you have to understand this in order to be able to tell it what to do, because it can't think its way through this. Yes?
So the only way to resolve V would need to have the seconds, right? You couldn't do that without knowing how much time it travels?
Well, you'll need some more information about the problem, and we'll deal with that tomorrow. But this thing here, you're using Vx is V cosine angle, VIY is V sine angle. That's the most you could do from this picture. But then you're going to take those and apply them in here somehow to start to eventually figure out how far did it go, or how high up did it go, or how long did it stay in the air. And if you're going, how, come back tomorrow.
Okay.
That was good. See, now that was the crescendo finish.